Okay. Please tell me what questions you have related to the chapters that we have discussed at linear algebra. Are there things that you want to discuss? Are there some types of problems that you don't know too well?
Yes, we can you make one more example with the direct sum?
Yes, of course. So let's take an example. We are talking about the sums. And I will want to make an example which is similar with the last example that you have seen at the seminar related to direct sums, which is an example involving also Euclidean vector spaces. So I'll combine Euclidean vector spaces with direct sums. And we'll consider a space W, which is actually the span of two vectors. Let's say V1, which is 1, 2, minus 1, 0, and V2, which is 0, 0, minus 2, and 4. First of all, you have to find W perpendicular, I mean the orthogonal complement of W, and then you have to prove that W in direct sum with W perpendicular is the entire space R the fourth, where W is of course a set, or better said, a subspace of this space. At the end of this session, I will put a PDF with the whiteboard on a conversation, so you will access this PDF whenever you want. So if you think that you understand better just by listening, it's okay. There is no need to write what I'm writing now. Also, I suppose that my connection is now very bad. So the ones who don't hear me, please tell me to repeat what I'm saying. Okay? Can you?
Okay.
Okay. So I need to find that perpendicular first, and then prove that uh, this sum is higher the first. But before solving this exercise, let's download the attendance list. Just a second. So I want to see who I'm talking to, and I will make a short check of the attendance list. Let me start. Just a second. Alcrinavia, are you here?
Yes, I'm here.
Okay. Gianna, I've talked to you. Georgiana
Yes, I'm here.
Spiridon? Georgiana?
Presento.
Moseini? Am I pronouncing correct?
Yeah, Hosseini. I'm
Okay,
Hosseini.
Hosseini. Okay, Hosseini. Much can you very
We can't really hear you.
Oh, yeah, just a second. Miruna, can you, do you hear me now? Okay. Let's move further. Page there is one. Sandu Laura? Okay. Gârbăcică Mihnea?
I'm here.
Okay. Harpa?
Present.
Popescu Emanuel?
Here.
And Miri. Ma- Oh, she's okay. So let's come back to our problem.
Also Beldia is here, but he doesn't have a mic. He wrote in
Okay,
chat.
okay. Oh, I'll check the messages then. I have seen that some messages appeared, sorry, on the chat, but I will check them later. Okay, so let's see how to solve the first point. What is the definition of perpendicular? Well, from first and from the last seminar, that this space is actually the space of all the vectors, let's say W, in this space, such that the vectors W are perpendicular to all the vectors V without the capital W. But do you need to that this inner product between all the vectors W general form and all the vectors from this capital W? Because in this capital W, you have an infinity number of vectors V, where you cannot compute an infinity number of dot products in this space. This condition is actually equivalent with what condition? Or what conditions? Well, using the fact that this space W is generated by V1 and V2, in this general condition, we write the fact that W must be perpendicular on V1 and V2. Okay, so we have that this is the set of all the vectors from the entire space, such that those vectors are perpendicular on V1 and also are perpendicular on V2. And this is because the fact that W is the vector space generated by V1 and V2. And let's take a look at these functions. Okay, take a look at the first condition. In where who is that? So W is a vector from R forth. So W is written as X, Y, Z, T. And in this case, this condition is equivalent
X plus 2y minus z equals 0.
exactly. And now we are looking at the second condition.
Sometimes we can't hear you, so that's why we We need to listen more to understand.
Okay. So, double this space. I hope that until the following session, I will solve this problem with the internet. It's not my fault. I'm so sorry. But I hope that this problem will be solved, so I will have a better connection next time. Okay, and this time you have to compute the dot product between W and V2, which is given by minus 2z plus 4t equals 0. Okay, so you have these two conditions, and then the system with these conditions. So from here, divide this equation by 2, you get that, for example, 2t. But, replacing here z by 2t will lead you to x plus 2y minus 2t equals 0. The idea is that you express z using t, and now you have to express another unknown from here, again using t and another unknown. So from here, let's say that x is 2t minus 2y. Okay, so if you denote t by alpha and y by beta, you have that x is actually equal to alpha minus 2 beta, and z is 2 alpha. Okay, this is the first method. We have solved this system directly, and here alpha and beta are in R. And the second method is based on the matrix associated to this system. So in the second method, you write matrix associated, which is 1, 2, minus 1 and 0, and 0, 0, minus 2 and 4. Actually, it's the matrix containing V1 and V2 on every line. So if you take a look at this minor, it is not given. So that of these two, and for the main variables will be the variables corresponding to these coefficients, which are z and t. Okay, so the idea is to express, for example, x and y using z and t. Here we have chosen this column and this one. So we have expressed x and z using t, but correct. Okay, so another method. But let's come back to our result obtained from method 1. And let's take a look at these solutions. So in this case, you have that this small vector w is formed with x, which is 2 alpha minus 2 beta, y, which is actually beta, z, which is 2 alpha, and t, which is alpha. Here, so in this case, you have that double perpendicular is the space of all these vectors, 2 alpha minus 2 beta, beta, 2 alpha and alpha, where of course alpha and beta are in. And this is perpendicular. This was the and if you have questions until now, do you have questions? No questions?
Until now, I think everything is clear.
I have a question.
Please.
So we can use any method to get to this form of W.
Yes, but depending on the method you will have of one or another. I mean that if you are using this method, you will have another expression for this vector. For example, you will have alpha or beta, 2 alpha plus beta, alpha minus beta, not necessarily this expression, but it doesn't matter.
Oh, so it's better. So it's good to make in any method. No.
Yes, any method is recommended because this expression doesn't matter because you will find different bases if you use different method. If you use this method, you find the base in the perpendicular, and if you're using this method, writing x and y, z and d, you'll find another basis, but both are correct. Because the space that you obtain using method 1 will be actually in the end the same with this one, because here alpha and beta can take any possible real value. So in the end, using the second method, you will see that at the same space. Okay, and other question? If let's move further, let's move to proof B. We have to prove that sum is actually out of four. What's a direct sum? What's direct sums? Or how did you prove that the entire space is a direct sum between two subspaces? Which is the definition of the direct sum?
The sum of the two spaces is in R4, and the intersection of the two spaces is the null vector.
Exactly. So, in order to prove that double sum, double perpendicular out of fourth, you have to do two things. First, their sum is this space, then the intersection is the vector of the space. Okay, let's talk about first fact. How to prove the sum of two subspaces is this space? You have here actually two methods. One that you have seen before studying basis and linearly independent system, and that method is based on double inclusion because you need to prove that two sets, because this is a set actually, that two sets are equal. So in order to prove that two sets are equal, you have to prove that each set is included in the other set. So method number one consists of proving this double inclusion. The first inclusion is obvious because you know that W is a subspace of R4, so it's a subspace. Also, you know that W perpendicular is a subspace of R4, so you know that the sum is also a subspace of R to the fourth. This is a theorem or property actually that we have seen at the course. So this inclusion is obvious. Okay, you have that this sum is included in R to the fourth. And now you have to prove that R to the fourth is included in W plus W perpendicular. But this is obvious. And what you should do in this case is the idea. So you have to take V of from R to the fourth, and we have to find V1 in W and V2 in W perpendicular, such that V is V1 plus V2. Okay, so it means that V1 prime and V2 prime, not V1 and V2, because we already have this notation V1. Okay, from the fact that V1 prime is W, you have that V1 prime has what form? How can you write V1 prime using the fact that it is a vector from W? Well, the W that is the span of V1 and V2. So using this fact that this is the span of V1 and V2, you have that V1 prime is actually a constant times V1 plus a constant times V2. Okay, so V1 prime will have this form. And then you will have to use the fact that W perpendicular has this form. So knowing that V2 prime is in this space will lead you to the conclusion that V2 prime is actually a vector having this form, 2 alpha minus 2 beta, beta, 2 alpha, and alpha. And now the idea is to find A alpha and beta. So you need to find them such that is V1 prime plus V2 prime. Okay, so you need to find these two vectors, which are these vectors, which is equivalent with the fact that you need to find these constants, A, B, alpha, and beta, such that V can be written as the sum of these two vectors. And of course, because of the fact that V is a vector in R to the fourth, it's F, Y, Z. Okay, so for X, Y, Z, T, you need to find B, alpha, and beta. So in the case, A, B, alpha, and beta depend on these unknowns, X, Y, Z, and D. But this is a method which takes you a lot of time. And in a test or in an exam, the time is very important. So we take another method that will help you to find faster the fact that this sum is the entire space. Okay, so let's move to method number 2. Again, for this first fact we need to prove. So we'll see method number 2. This method number 2 is based on the fact that you already know a possible basis of W, and you would find very easily a basis of W perpendicular. So basis of W and W perpendicular, then you could take a look at the set with all the elements from both bases and to prove that the set is actually a basis in this space. So now the first step is to find the basis in W. Okay, I need the basis in W. How do I find the basis? How do I find the basis? So that is span of V1, V2. So in this case, V2 is what for W? This set. What is this set for W? It is called generating.
Oh.
Not actually. I don't know if they are independent or not. I know for sure that they form a generating system of W. Okay, and now I want to see if this is a basis. So I need to see what? I need to check that.
It is
V1
linear
and V2 are-
independent.
Yes, I need to check if they're independent. So in order to check if they're independent, I have to write the matrix containing these two vectors, V1 on this column, or on the first line, actually it doesn't matter here, and V2 on the second column. And let's take a look again at the vectors, 1, 2, minus 1, 0. So 2, minus 1, 0. And 2, 4. Oh, and we have seen this matrix when we solve this system using the method number 2. So this matrix is the rank equal to 2. You know this fact. You always know this fact. Okay, the rank is, for example, given by this minor of order 2. So you have that rank of A is 2. So it means that V1 and V2 is a really independent system. Okay, let's use this data. This data is not twice. And so it's denoted by double star. So from and double star, we have that the set formed with V1 and V2 is a basis in W. So we have found the basis in W, and the dimension of W over 1 in this case is Q. The dimension is okay, because you have vectors in this basis. Now, let's find the basis in W perpendicular. How do we find the basis in this space? Well, look at the vectors from W perpendicular. You know that this space is the space of all the vectors having the form 2 alpha minus 2 beta. Okay, this is the first element. Beta to alpha and alpha. So actually, W perpendicular can be written as the space of the vectors which can be put it in the form of a sum. And the first vector will contain only alpha, and the second one will contain only beta. For example, three parameters, alpha, beta, and gamma, then you will have to write this vector as the sum of 3 vectors. The first one depending only on alpha, the second one depending only on beta, and the last one depending only on gamma. But because of the fact that you have here 2 parameters, you have to write this vector as a sum of 2 vectors. The first depending only of alpha, which is 2 alpha, 0, 2 alpha and alpha. And the second one depending only on beta. So you have -2 beta, beta 0 and 0 alpha, beta, alpha. So this W perpendicular is actually the space which looks in between. Let's note this one by 1 and this one by W2. So it's that the perpendicular is actually the span of which vectors? So W perpendicular is the span of, can you hear me?
Yeah, but not very good.
Okay, this is the span of
The span of W1 and W2.
exactly. Okay, so I will try not to put so many questions if you cannot hear me well. I will explain and it's better for you to ask me instead of asking you. Okay, so this is the span of W1 and W2. So it means from here, it means that W1 and W2 is this span of, okay, so we have here genetic system, and to obtain a basis, we have to check if the system is linearly independent. So I'm taking this matrix, which takes W1 and W2. Okay, the of this matrix is 2. So it means that you have a linearly independent system. Okay, and simple and for you have that the set W1, W2 is a basis in this space. And of course, the dimension of R of the space is 2. Okay. Now we found basis in W, we have found basis in W perpendicular. So in order to prove that R perpendicular is that space, we have to prove that the square root is 2 and 2, which is actually the basis of the view, and W1 and W2 is a basis in R other 4. Okay. How do you prove this one is a basis? How do you prove this fact? So you have to
We have to prove that it's a generating system, and it is already, and that it's linearly independent, and we do with a matrix of 4 by 4, and then we
yes,
get
but
it.
you don't know that this system is a generating system. This is the idea, to prove that it generates the entire space. But in this case, there is no need to prove that this is a generating system, because you have a theorem that you have seen at the course, which tells you the following fact. If of K is space of dimension equal to and V is a linear independent system including V, and V1 Vn is a basis of V. Okay, so the vector space of dimension n, and you have a set with n vectors. This is the idea, to have a set with n vectors which are linearly independent in this space. Then you will have that this set is a basis without proving the fact that this set is a generating system. So it is a shortcut, actually. And in order to prove that this is a basis, we'll just take a look at the matrix formed with V1, V2, W1, calligraphic W1, and W2. And if the rank of this matrix is 4, then it depends. And because the dimension of this space is 4, then it is that it is automatically a basis. Okay, so I need to put the matrix. And I will let you 2 minutes to find the rank of C. And in order to find the rank of C, you have to find the determinant of C to see if it is equal or not to 0. Okay, to the determinant of C, and then you tell me the value of this determinant and how you solve.
Minus 58.
Have you obtained the same result as your colleague?
Yes, minus 58, same
Yes.
result.
Okay. All of you know how to find the value of this determinant?
You will
Pardon me.
you will subtract the 2 times last column from the first one, and you will get zeros.
Exactly. You could use actually you could use this line or this column. Let's say that we want to put zeros here. So the idea is to obtain zero here, for example, or here, it doesn't matter. If I want to obtain a zero here, I have to add 2 times the first column at this one. So I have 0, and then I will develop this determinant using this column. Sorry, I have to add some lines to obtain here 0. Okay, so if you want a computation,
But I think it's not good to add the first line to the last, because we'll get -1 on the third position.
No, I think that I'm sorry, I was pronouncing wrongly something. The idea was to add some lines, not columns.
Oh,
I have
okay.
said column instead of line. So 2, 0, or 2 and 1. Okay, so take 0 here. So this is to use the first line, not first. I have wrong the column. Is just the first line and the second line. Okay, this was my idea to add at line number 1 2 times line number 2. So you will have 2, 0, 0, 1 here, -1, -2, 2, 0, 0, 1, 0. And have this one, which is 5, 0, 2, and 0. So you take this one, which contains only 1, so you have 1 times -1 at this is line number 2 and column number 4 times, and now you cut this line and 4. So 5, 2, -1, -2, 4. And from here it's very easy. And I'll use your computations, and I'll write here -15. Okay, so the idea is that this determinant is not 0, and using this fact you have that rank of C is 4, and because rank of C is 4, you have that V1, V2, W1, W2 is linearly independent system. And use this theorem and the fact that you have here 4 vectors and the fact that the dimension of this space is 4, you have that this set is actually a basis for R4. So I'm going to write the details. You have that again, V1, V2, W1, W2, linearly independent system. It's linear. Here you have 4 vectors. The dimension of this space is 4. So you have that this set of 1, 4. It is that W plus W perpendicular is R out of 4. Although it seems that the second method is longer, Actually, it is not complicated because it took me some time to write the details, but in an exam you will write very fast these details. There are actually some things which must be stated. You have not so many computations as you had in the first method. So you just have to compute some determinants, some minors, to state a rank, and to conclude that the sum is correct. Here I have written with details. And, this is the which so much to solve this problem, but when you are using method 1, you will have a lot of computations to do because you have to solve 4 times 4 system, and you have to express all these unknowns A, B, alpha, and beta using X, Y, Z, T. So it will actually take you a lot of time to solve it. And if you are wrong with your computations, try to use the method you like the most. But for me, I prefer the second method. Okay, so this was the first step. Okay, this was the first step in which we proved that the sum is the entire space. And now let's take a look at this step, where we need to prove that the intersection is the null vector. And again, I will use two methods. So we prove that the intersection by double perpendicular is the null. One consists of this equality as equality of set. So you know that the null vector is actually included in W, and also it is included in W perpendicular. So you know that this null vector will be included in the intersection of these spaces. Then you have to prove the intersection by W perpendicular is set. And a vector V from here. So let V of vector the intersection of these spaces, and you have to prove that V is actually the null vector. I mean that V is here. So it means that V is in W, V is in W perpendicular, and from here you have that V can be written as a linear combination of the elements from the basis of W, which is V1, V2. So it is equal to A V1 plus B V2. And from here, combination of from the basis of space, which is W1, W2. So this is CW1 plus DW2. Because you have the same vector here and here, it means that these expressions are equal. So you have that AV1 plus BV2 is CW1 plus DW2. Now we'll move all the terms from the right side into the left side, and we have AV1 plus DV2 DW1 minus DW2. But here combination of vectors, you will write here 0 because this is correct. You will write here 0, 0, 0, 0. I mean the null vector. But you have combination which is equal to 0. And you know that V1, V2, W1, and W2 are linearly independent. So, what is your conclusion?
That A, B, C, and D are equal to 0.
Exactly. Exactly. They must be equal to 0 because these values are independent and that is the calculation. So A is B is C is D is 0. So it means that replacing them in the first or the second form, you will have that V is the null vector, and this is what we wanted to obtain. So we have that the both inclusions are true, and in the end, you have that the intersection is the null vector. Okay, this was the first method. Do you have questions until
No,
now?
it's clear.
If you don't have questions, let's see the second method. The second method is based on a theorem related to management. And this theorem tells you the following thing. If W1 plus W2 is V, then the dimension of V is the dimension of W1 plus the dimension of W2 minus the dimension of the intersection between W1 and W2. And here, the dimension of V is actually equal to dimension of W1 plus W2. Okay, so the dimension of a sum is given by this expression. This is the idea. In our case, W1 is W and W2 is W. I think that there is no need for W1 and W2 to be orthogonal complements. So they don't need to be perpendicular as vector subspaces. They can be any vector subspace. And this theorem is true. So W1 is this space, W2 is this one. We have that dimension of W plus W perpendicular is actually from this theorem given by the dimension of W plus the dimension of W perpendicular minus the dimension of the intersection. At the first point, you have proved that W plus W perpendicular is R the. So you know that the dimension of W plus W perpendicular will be the dimension of this space, which is 4. Also, you know that the dimension of W is 2, and the dimension of W perpendicular is 2. So using these facts and replacing the dimensions in this equation, you will have that this dimension, which is 4, will be equal to this dimension, which is 2, plus this one, which is 2, minus the dimension of the intersection. So it means that the dimension of the intersection is 0. And if the dimension of a space is 0, it means that the space is just
The null vector.
this. But the is that. Again, you can choose any method you want, but make sure that you're incorrect the statements. Okay, any questions?
No, it's clear.
Okay, then another type of problem that gives you difficulties. Or if you have questions related to the theory or to what you have seen at the seminar.
I have a problem not related to this. I have to go now, but is there a problem if I leave and just take the course from Teams?
Okay, I have a question first, right?
No, the thing is I have to go. I can't stay any longer because I have to catch a subway, but I want to take the course from Teams. Can I leave and take the second problem from Teams when you post it?
Can you please write your question in chat because I don't understand very well what you're saying. The quality of the sound is not so good, so I don't understand each word that you're pronouncing. Can you
I will,
please write?
yes, I will right now.
Okay, I'm waiting. Okay, let's come back to Skype.
I have another question if
Yes.
nobody has a question. So I don't really understand how to prove, um, let's say, a polynomial with real coefficients of rank n. It's an inner
Okay.
product.
So you are just to take a look at your homework.
Yeah, I try to make the for homework because we have sometimes, but I don't really understand if it's good or not what I made there.
Okay, just a second. Let me find. But I think that will take some time. Can you please tell me which exactly was that? So about inner products,
Yes.
you are
Um, what?
well, you have two polynomials P and Q in R. What degree? N?
N, but we say that n equals 3.
R X, and you have to prove that this function given by plus P1 K1 plus P2 Q2 plus P3 Q3 is in bracket.
What?
So you have to prove
Yes,
that.
it's an inner product.
Okay. So in this case, I should write more specific the fact that are polynomials in this way. So P0 plus P1 times the whole, which is x from here, plus P2x squared plus P3x cubed, and Q is Q0 plus q1x plus q2x squared plus q3x the cube. Okay, so you form and you have this function defined in this way. It gives you the product and then the sum of the produces, and you have to prove that this function defines an inner product. Okay, so in order to have an inner product, you must some statements. Okay, and I will write them different. So first you have to know so p plus let's say you another letter r. Okay, p plus r and q is pq plus rq, where every p, q, and r polynomial with 3, you have to that alpha times p and q is actually alpha times pq for every pq polynomials and alpha a constant, a real constant, because this space is a vector space over R. You have to prove that QP is actually the complex conjugate of PQ for every P and Q in R3 of X. And in the end, you have to prove that P dot product with itself is greater than 0 for every P polynomial different from the null polynomial. Okay, so P must be 0, 0, 0, 0. So let's discuss about that. Janan, where you had difficulties? Or where are you not sure that
So I am not sure at what to pick. So here, for example, if I go, let's take any property. Let's say first. How do you pick? You write like p equals p0 plus p1 x.
Yes.
No.
Yes. So you take p a polynomial of 0 plus qx plus p squared plus p3 x cubed. Then q again having this form. This is the same, and r is r0 plus r1x plus r2x squared plus r3x cubed. And then you compute p plus r, okay? P plus r is actually the polynomial given by p0 plus r0, oh sorry, plus p1 plus r1 x plus p2 plus x2 x squared plus p3 plus r3 x cubed. This is the first one. And second one is which will be done here. Okay, now when you compute this product, you have to do the functions. Not compute the inner product of two polynomials. You just multiply the corresponding coefficients and then add what you obtained. So you have to multiply this one because this is the free term with this one, and you have p0 plus r0 times q0. Then, so this was the first one actually. Plus, I have to add, I have to express this one, So I have plus Q times Q1. I have to write plus from here this one with this one, P2 plus R2 times Q2 plus the last one, P3 plus R3 times Q3. Okay. And after that, you have to multiply Q0, Q1, and so on with each bracket. So you will have P0, Q0 plus R0, Q0 plus, this was the first bracket from here, plus P1 plus arrow Q1, the second, and so on. Okay, and now I will try it again, but I circle the terms that will be grouped. So I have to group this one and this one, and oh, sorry, not this one. I missed a term. This one with this one with this one and with this one. But then I have to use again the definition of the inner product. So actually the sum of this terms, this one plus this one plus this one plus this one, will be equal to P Q. The rest of this one plus this one plus this one plus this one is actually the inner product of R and Q. So I start with this one. Okay. And I obtained that it is the sum of these inner products. So the first statement is proved. And all of them will be similar. So problem, I need to prove two first one.
No, it's good. Thanks.
I have a question. This may be stupid, but where did the x's go? So we have x at the power of 2, x at the power of 3, and then they just disappeared. I don't really understand why.
They disappear because this is the definition. If I define this function in this way, this function will check all these four properties. So it will be an inner product. This was the definition I did for this function to look like this. This is not a theorem. I just have defined this function in this way. Okay, I have the right to define any function in each way I want to. So I have chosen that this function denoted in this way is equal to sum. As you choose f of x to be equal to natural logarithm of x, in the same manner, I have chosen this sum to be equal to this expression. And this will be actually an inner product, so it will be a function which will have these properties. But it is just a definition. So
Okay, I understand. Thank you.
other questions. The idea is that to answer your questions, because if I'm writing solutions for some problems, I'm not quite sure that the problems that I choose are actually the problems that give you difficulties. So the idea is to come you and to ask me some things that you didn't understand. Because otherwise I could solve problems till tomorrow. But the idea is to cover those type of problems that you're not so so then we want to work. What problem you want to solve? What questions?
I have another question. It is a shorter way to find out if a vector is a linear combination of other n vectors.
Not actually. The general case, no. In the general case, you have a vector v, and you have another set of vectors v1, v2, vn. If you want to see if v is a linear combination of v1, v2, vn, you have to find the constants a1, a2, an, such v is the linear combination of
And
v1,
you have
v2, vn.
you have a lot of computations.
Yes, you have a lot of computations, but if you have particular cases, then maybe then you could find the writing of v, the combination of the vectors, see some facts, but only in particular cases. In that case, no, if you have such example, if you have one that you want to discuss with, you could tell me the problem. Do you have a particular case? Do you have an example? Or it was just a general question?
I have an example if you want to say.
Sure, of course.
Okay, I have now on the screen here. I read it or
Just tell me.
okay, so we have a vector v
Yes.
with 1, -2, 0, 3 in R4, and you have to find out if it's a linear combination of vectors. U1 equals 3, 9, -4, -2. U2 2, 3, 0, -1. And the last one, U3 equals 2, -1, 2, 1.
This case, the only thought help you is to notice that maybe U1 plus U2 minus 2U3 will give you this one, but it is just a fact which is based on a remark. I mean that if you notice that a linear combination of those vectors will lead you to V, you should write it. But otherwise, you have to find. So the question is if V is in the span of 1, 2, 3, right?
Yes.
You have to find A, B, C in R such that the V is A, B, plus B, plus C. Actually, seeing that V is in this span doesn't imply necessary the finding of A, B, and C. I have written here that you have to find A, B, and C, but actually the problem is that you must see if A, B, and C exist such that V is this one. So A and C exist such that V is this one. And it's a difference because means solving the system and writing exactly V as a linear combination, but seeing if these constants exist is equivalent with seeing if this system is compatible or not, but not solving it. So if the question is if V in this then the answer should be based on the fact that you have to study the compatibility of this system. If the problem tells you to write V using U1, U2, and U3, you have to solve the system. Okay, so if you want to see exactly ABC, you have to solve the system. If you want to see just if V is in this span, you have to see if the system has solution. And your question is just this one, or do you want to find A, B, and C?
No, my question was if it's a faster way than finding A, B, C.
No, finding ABC, that's not in this case. You have to find ABC.
Okay.
Okay,
Thanks.
so you have welcome. You have to write a system and find them. If your question was how do I check if V is in span, then my answer is don't find ABC. Just see if the system is compatible. If you don't have a word to find.
Okay, but the system needs only to be compatible, so it can have an infinite solution or only one.
If you want 2, 3 vectors in R4, yeah, if not basis, but they cannot be a basis because the dimension of R is 4. You could have more possible solutions, maybe. Let's see. But what happens in this case? So if you have 4 vectors here, or U1, U2, U3, and U4, which form actually of 4, but if you take this plan and U1, U2, U3 are independent, you will have actually keep writing. It depends actually. If U1, U2, and U3 are not independent, you have multiple solutions. It depends a lot if they're independent or not. This is the idea. So this is why I've told you that you may have or maybe not an infinite number of solutions. Let's see what happens in this case. So you have to write V, which is 1 minus 2, 0, 3. You have to, I'm writing it this way. As 8 is U1, I think 3 minus 4 minus 2 to see what this is plus 3 times 2, 3, 0, minus 1 plus C times 2 minus 1, 2, 1. So you have a system which is 1 minus 2, 0, 3. I'm writing directly the equations. This is why I wanted to write them this way. 3 plus 2 plus 2, 3. This is 9 plus 3b minus c. This is minus 4 plus 2c. And this is 2a minus b plus c. Now, what type of system do you have here? With how many equations and how many unknowns?
We have four unknowns, 4 equations.
Actually, you have just 3 unknowns, 3 variables.
Oh yes, because
and equations. So possible that the system is incompatible, or the system may have a unique solution, or the system may be compatible with an infinite number of solutions. It depends. For example, if the system is uncompatible, then U is not in this span. If the system has just a solution, then we can cut an equation from here and use the other 3. And if the system has an infinite number of solutions, you could cut 2 or 3 equations from here. That is why I've told you that the type of this system depends on how these vectors are, dependent or independent. because the dependence of some vectors is equivalent with the value of the rank of the matrix with those vectors. So if the rank of this matrix is the maximum possible, the system could be compatible or compatible with the solution. If the rank of the solution matrix is 2, 1, then the system has an infinite number of solutions. It depends. You have to make the computations. Until you don't make computations, you won't see the so do you want to go to this now? Do you want to see in which case we are?
Yes.
Okay, so let's see. You have the matrix associated to this system, which is actually the matrix given by these vectors. This is why I wanted to write on the column to see better that the column of the matrix associated to this system is actually the matrix in which you put U1, U2, and U3 on each column. So the matrix is A, three, four, two, two, three, zero, two, minus one, one. Oh, maximum value for the rank of A is 3. Okay, I still want to find the rank of A. How do I find, in this case, the rank of this matrix? Well, I have to use the fact that this matrix has 4 lines and 3 columns, so I cannot compute a determinant for this matrix. Okay, I'm forced to find minors, which are not 0. Let's start with this one, for example. This delta 1, which is 3, 2, 9, and 3, which is minus 9, which is not 0. So the rank of A is at least 2. Let's see if we can find the rank of 1, 3, which is not 0. Have 3, 2, 2, 3, minus 1, minus 4, 0, and 2. And this is 18. Please follow computation. So I thought I see the message. You have 18 plus 0 plus 8 from here, right? Minus, I mean, plus 24 from here, 0 from here, and minus 4 times 9 is 36. So I have 26 plus 24, which is 50, minus 36 is 40, which is not 0. So it means that rank of A is 3. And because I have used this delta 2 to find the rank of the matrix, it means that the last equation of the system, the equation which corresponds to this line, gives me some problems, because this equation makes the difference between uncompatible system and determined compatible system. So this is the line which gives me problems, and this line will split this problem into 2 cases. If I have an independent compatible system, or compatible, I'm useful. So in this case now, you cannot have an infinity number of solutions. For example, if all the minors of order 3 were 0, then the rank of A would be 2. So if the rank of A is 2, it means that you will have to cut the equations and then take a look at this system formed with the first two equations and solve it. But having two equations and three unknowns will lead you to the fact that C is a secondary variable, so you have an infinity number of solutions. Okay, is it clear?
Yes.
Okay, but now you will have no solution or just a solution. What you should do to see in this case or this one? How do you make the difference between these two cases? And this question is for all of you, not only for your colleague, Jonah. How do I make the difference between these two cases?
So the difference between two cases is when you compute the determinant, if it's 0, then it's oh no, sorry. So
yes, that's the determinant. You're totally correct. Telling me, not the determinant of this matrix, the determinant of the extended matrix.
matrix, yes.
Yes, this is correct. Okay, tell me.
Okay, so if you compute and it's 0,
Yes.
then the system enters in other two possibilities. So we can have an infinite solution or it can be incompatible.
Just a second. If you take the extended matrix, if you compute its determinant and see that it is 0, it means that the rank of the extended matrix will be equal, not 4, because the determinant is 0, but the rank will be equal to?
Rank of the matrix.
Yes,
Of the
the rank
system
will
matrix.
be
3.
equal to 3 because this matrix contains A. And because it contains A, you already have a minor of order 3, which is not zero. So if this happens, that it means that the rank of A is 3, the rank of the matrix is 3, but also the rank of A is 3. So using this fact, you have that rank of the extended matrix is rank of A. So it means that the system is compatible and it has a unique solution. I mean that you are in this case. The system is compatible and more precise solution. Because in this case, you're taking a look at the system on 3 equations, and because the determinant that gives me the is formed with the first 3 equations, I'm taking the first 3 equations, I cut the last equation, and I'm solving the system formed only with the first 3 equations. So in this case, I will take a look at the system formed with just 3 equations. I'm cutting the last one, because the last one is a linear combination of this one. So in this case, I have 3 unknowns, 3 equations, and the rank of the matrix associated is 3. So I have a compatible determined system, unique solution. Okay, so you want to have a case when you apply so what happens if the of extended matrix is not 0? Then rank of the extended matrix will be
4, and that means it's incompatible.
exactly. So using theorem, gonna get out. You that the rank of n is not A, system. So it means that V is not in the span of U1, U2, U3. And now you have to write the extended matrix and to find its determinant. Okay, let's have a 4 minutes break. And after that, if you succeeded to find the value of the determinant, you tell me. If not, I'll let you 2 or 3 more minutes to find the determinant, okay? So let's okay, I'm back. Did you manage to find the determinant, or you want to let you 2 or 3 minutes to find it?
Yes, the determinant is 0.
Okay, perfect. So being 0, it means that you are in this case. So your system is compatible. So you can write V in a unique way using U1, U2, and U3. So you have a unique write. Unique solution is equivalent with unique writing of V in terms of U1, U2, U3. So do you see that the fact that the rank is 3 is equivalent with the fact that U1, U2, U3 are independent. So if they are independent vectors, it means that you will have a unique solution or not, or you want a solution. And if they're not independent, so this is equivalent with the fact that you don't have an independent system of vectors, you have a unique solution. But the independence will apply to U1, U2, U3, and the free terms column. So you have to see if U1, U2, U3, and the free term column, which is B, which could be a U3. If all these four vectors are independent, it means that you are in this case, so you don't have solution. Okay, it depends a lot. It depends a lot on the rank, which represent with the depend vectors from A and of course the dependent vectors. So you could have a possible situation here. This is the idea. Do you have questions related to this problem?
No.
Okay. Or question. Or other question. From participants, not from also general the question. Or what seems difficult in this subject? What would the difficulties in algebra?
Could you please repeat?
Yes, what difficulties have the linear algebra? What appears to be difficult in this subject?
Mm,
subspace. Let me give you an example to talk based on this example. Let's start set of vectors in the fourth such that x plus y minus 2z is 0. X minus t is also 0. 2y plus z minus t is also 0. A. Prove that W is a subspace of R to the fourth. B. Find a basis of W and the dimension over R of W. Okay, let's see the first point. What you should prove about W? Well, you have here two methods. Method 1, based on definition. And this method tells you that if you manage to prove that V1 plus V2 is a vector from W from every V1 and V2 in W, and if alpha V1 is W for every V1 in W and in the set of scalars, which is R, then W is a subspace of this vector space. And method 2, based on a property, which tells that W is subspace of R4 if and only if alpha V1 plus beta V2 is in W for every V1 and V2 in W and alpha and beta in R. But how would you do in this case? Let's say that we choose method number 2, okay, and we are using this property. What you should do? Well, in this case, if you take V1, V2, two vectors from W, you have to check these conditions for this vector. Checking these conditions for this vector will take you a lot of time, and there is the risk of making some mistakes in your computations. So my advice is to first solve this system and then to write a more specific form for W. And after that, choose a method and try to prove that W is a subspace. But first of all, try to rewrite. So if you try W, this x minus 2 x minus t is 0 and y plus b minus t is also. What type of system is this one?
It's a homogeneous system.
Yes, homogeneous system. So you will have at least the null solution, and now you have to see if you have other solutions. So my advice is to write the matrix of the system, which in this case is 1, 1 minus 2, and 0. And then you have 1, 0, 0 minus 1, and 0, 2, 1 minus 1. Okay, this is the matrix. I have parameters x, y, z, t. Please find the rank of this matrix. Okay, to find the rank.
The rank is free.
Sorry, can you repeat, please?
The rank of this matrix is free.
Okay, because you took what minor?
The first three columns until there, until
Yes,
minus 2,
yes.
0, 1.
If determinant using the first three columns, using the step 5, actually, you see that it is not 0, so rank of A is 3. So it means that you have how many main variables? How many main variables do you have?
3 main variables and 1 secondary.
Yes. Yeah, so T is secondary variable. So T is 1 and B. And let's do this thing that x plus y minus 2z is 0. Also x minus alpha is 0. And 2y plus z minus alpha. So 2y plus z minus alpha is 0. Okay, from here x is alpha. Sorry. So I have that, first of all, x is alpha. Then alpha plus y minus 2z is 0. And then 2y plus z minus alpha is 0. What we should do with these two equations?
We can multiply the last one with 2 and make the addition between them.
Yeah, exactly. So I have alpha plus y minus 4y from here plus 2z minus 2y 0. So I have that 5y is actually alpha because this is minus alpha. So y is 1.5 times alpha. Okay, and now I'm taking a look in the first equation from these two. So I have that alpha plus y minus 2z is 0. So I have that alpha plus alpha over 5 is 2z. So I have here 6 over 5, so z is 3 alpha over 5. And x is alpha, t was also alpha. So in this case, space W is actually the space of all the vectors which look in this way. Instead of x, I'm writing alpha. Okay, y is 1 over 5 times alpha. You have 3 alpha over 5 instead of z, and t was divided by alpha, of course, by r. And then space divided by alpha times 1 over 5, 3 over 5, and 1 with alpha in r. But if you don't like this writing because you have here fractions, you could write an alpha over 5 in front of this vector, and you have 5, 1, 3, and 5 again with alpha real. Okay, and you should denote this one by your beta, let's say. So this is actually beta times 5, 1, 3, 5. Beta is alpha is so so space W in our case is this one. And now that we have found a better form of W, let's see if W is a subspace of R3. Okay, I'm writing again W. So W is beta times 5135, 513. So take one W. So first of all, V1 will have the form that times 5135. Okay, and V2 will have the form beta 2 times 5135. So if you add them, you have that V1 plus V2 is beta 1 plus beta 2 times this vector 5, 1, 3, 5. Using the fact that 1 and V2 are in W, it means that beta 1 is in R, so I have this condition checked. This is also in W, so beta 2 is in R. So having these facts, I have that beta 2 plus beta 1 is also in R. Okay, so something from it could be gamma if you like. So you have something in R times 5, 1, 3, 5. Is this vector or not? Is this one in W?
Yes.
Yes, of course, because you have a number times 5, 1, 3, 5. All the vectors from W are written as a real number times 5, 1, 3, 5. So, yes, this is in W. Okay, so you have that V1 plus V2 is in W. Then you take V1, which is the same V1 is 5, 1, 3, 5 with beta in and outside when you compute alpha times V1, you have that this is equal to alpha times beta 1 times 5, 1, 3, 5. So this is a real number. It could be denoted by gamma 1, gamma 2, C1, it doesn't matter. You have a real number times 5, 1, 3, 5. It is a vector from W. Okay, so alpha V1 is in W. No matter how V1 looks like, and no matter the value of alpha. And here you have this equality, no matter in the. So this one Yeah, the space of R. That's questions are
No, it's clear.
so it's good to B because this was point one. I had to prove that W subspace. Okay, was point one. We have to find the basis of W and we have to find the dimension of W over R. So again, we won't take a look at this one. We'll take a look at this one. Okay, for B. I'm writing again that W is the space of all the vectors having this form 5, 1, 3, 5. With beta in R. No, is space of what you could extract from here. From this form. What could you extract? What information do you have from the definition of W? From this definition? Generating system.
Yes, it's a generating system.
Yes. A generating system for W. Do you know a generating system?
No.
Yes, you know. This one. W. Because all vectors from W can be written as a time this vector. So this vector generates me all the elements from W. Actually, W can be written as the span of W1. This is the definition of the span. This is the set formed with a constant times this vector. So it means that the generating system of W. But if we want a linearly independent vector, is W1 independent vector?
Yes, it is.
It is because W1 is not the null vector. So being different from the null vector, it means that the system formed with V1 is only independent system. From start and you have that formed W1 is actually this of so it means that the dimension of W for E is because you have just a vector in the basis. Okay, is it clear or not? Do you have questions related to what I'm here?
It's clear.
Okay, so let's see again who have talked to. So I'll take a look again at the list and then we'll finish this session. Just a second. Oh, you are more persons. Alkina, Adam?
Yes, I'm here.
Okay, Omer, you are present because you
Yes, I'm
have
here.
talked to me. Spiridon, Georgiana, you left. Okay. Hosseini,
Yes.
hello again. Okay. Just that. Dear also, San,
Present.
but
I'm here.
perfect. Harpa.
Present.
Okay. Popescu, Emmanuel, you have also talked to me, but I see that you're not here now, okay? And your colleague also left. And
Present.
Slide,
Here.
was the final example okay for you?
Yeah, thank you.
Okay, you're welcome. Alexandra, Rus, are you here?
Yes.
Okay, and Anna Fekete?
Present.
Questions, please without questions, and you tell me in the next session, because the idea of these sessions is to answer to your questions and also try to suggest me problems that you would like to see solved, okay?
Okay.
Thank you for participation. Have a nice day and have a nice week too. See you next week. Goodbye.
Goodbye. Have a nice day.
Goodbye.
Thank
Thank
you.
you.
Bye.
Bye.
Goodbye.